Today's topic is exclusive lock versus shared lock, a very common topic out there in the database and the DBMS systems. So let's start with, in this episode, we're going to discuss the differences between them, and we're going to talk about an example, some advantages, disadvantages of both, and we're going to talk about an example. So let's start about defining each of them. So exclusive lock and a shared lock. So think of an exclusive lock as following. I wanted to read a piece of data in my database. Think of it like a column or a row, but I want to make sure that when I read this value or when I want to update this value, nobody is connected and nobody is attempting to read this value. For security reasons, for consistency reasons, I want to acquire an exclusive privileges on this value, on this column, on this row, so that if anybody tried to read that value, they'll get an error. So you know what? So that's the idea of an exclusive lock. So I will be the only one, essentially, as a connection. I'll be the only one who's allowed to update that, so nobody can sneak in and start reading values out of that. All right. The shared lock, on the other hand, is actually the opposite of that. Is when I want to read a value from the database, when I read a certain value, I want to make sure that nobody changed that. So if I am reading my balance in a bank, right, I want to make sure I'm doing reporting, I'm doing a huge query, I want to acquire a shared lock and says, hey, database, please, I'm acquiring a shared lock on this row. So if anybody's trying to edit that value, just make them fail. So I want this value to be always the same in my vision, in my transaction, in this current transaction. I want it to be unchanged. That's why I acquire a shared lock. And many users can acquire, many connections can acquire different shared lock. I know this might sound a little vague, but we'll explain it in an example, hopefully. So let's get to an example. So exclusive lock, general, I want to obtain a lock on a value, so I am the only one who is allowed to edit it. Shared lock, I want to acquire a shared lock on, or a read lock on a value, so it doesn't change. So another thing I want to explain before we go to the example is when I try to obtain an exclusive lock, there must not be any shared lock acquired on that value. Does that make sense? So they are linked actually together. And the opposite, if I want to obtain a shared lock, there must not be any exclusive lock obtained. So these two are exactly the opposite of each other. So you can have, as let's say for example, I have like 7 shared lock on the balance on a certain value. That means nobody can acquire an exclusive lock on that value, so nobody can edit it as a sense, So that's the idea, read or write lock. That makes sense. Let's jump to an example, guys. All right, so here I have 3 people, Alice, Bob, and Charlie. Alice is red, Bob is blue, Charlie is green. And we're gonna start, this is the timeline from left to right, and then we're gonna start with Alice started the transaction trying to deposit $200 on her account, right? So in order to do that, she needs obviously to do an update statement, right? To do that, you need to acquire an exclusive lock. And guess what? She's the only one. Seems she's the only one that is connected right now. So she'll basically tries to acquire an exclusive lock, and guess what? It succeeds because nobody else acquired any shared lock, so they're good. It's just like move on, and she acquired the exclusive lock. Now she's guaranteeing that, hey, I'm about edited, and that's good because I don't want people reading bad value, right? Because I'm about to update this balance, so don't ever try to read my balance right now, because it's gonna change. If you read it and make decisions based on that, it's gonna be bad. All right, so you're gonna acquire that, and then it says, okay, I'm gonna deposit. So the next transaction is essentially transaction gonna commit, and then she's gonna increase her balance by 200. Very, very quick. And then commit the transaction, and then her transaction finished, right? It's just that short period of time. And then she turned around, Alice, and then starts another long-running transaction. Look at that. It's a long transaction, looks like it, right? It's a job, reporting job. On her balance, she's doing reading a lot. She's just doing reading operations. So a read operation is acquiring shared log. So what she says here, says, hey guys, I am going to acquire a shared log on my balance account. So don't try to change it, please. Don't try to mess with it. Don't try to update it, because you can't, because I just acquired a shared log. So nobody can acquire an exclusive log on her account now, because she just had a shared log there. Okay, makes sense? So okay, she's doing her thing, or reading all these tables and doing the reporting. So very long transaction, when Bob started another reporting job on his account. So that's a completely different thing, right? So they acquired a shared log. Bob acquired a shared log on his account, so on this value, while Alice acquired a shared log on this value. Make sense? All right, so that succeeded. We have a log for Bob, we have a shared log for Alice, and then we're continuing. So something is gonna happen here. What is the green thing? What is going on? Charlie, what are you going to do? Charlie wants to do a transfer to Bob's account. Bob, it's your lucky day, dude. Bob's account attempt to obtain an exclusive log, but fails. Why? Because he want to do a transfer, right, from his account of a $300. I didn't write it there, but trying to do a $300 transfer from Charlie's account, from his account to Bob's account. So in order to do that, he needs to acquire an exclusive log. So he's saying, I want to update that. Guys, I don't want you to change that. So Bob we try to acquire an exclusive log on Bob's account, and he says, oh, fails. Why? Because Bob has already acquired a shared log. He's doing something. He's doing his thing. Bob is doing his job. He's reading all these tables. He's doing a thing. So he asked us to create this shared log so nobody changes his account. So guess what? Charlie just failed his transaction. He cannot do that, and that's actually good. We don't want people editing while other people are reading. It's just so that's dangerous, especially with banking systems. So guess what? After a while, Bob completes his transaction, his job, his reading job, and he says, you know what, I'm done. So he releases that shared log, so he's no longer acquiring shared log. Afterwards, Charlie attempts again to acquire exclusive log, and this time he succeeds. He says, okay, since I just succeeded, let me quickly go ahead and acquire the exclusive log, and then commit the $300 from Charlie's account to Bob, right? So that's the differences between exclusive log and shared log. And there's another example that I didn't mention here, is like while there is an exclusive log, nobody can read. So you can think of this, that let's jump to the disadvantages and advantages of all this thing. Is shared log and exclusive log was introduced to ensure consistency in the system. As you can see, right, I want to be consistent. When I read this value, I wanted this value to always be the same. That's a shared log. Exclusive, when I want to write something, I want nobody to be connected, right? So next time they connect, they read the latest value. And exclusive log and shared log in general, they are very useful to obtain consistency, especially with banking first, and the second thing is with configurations. If like you have a central configuration system and it's a critical configuration system obviously, and you're making changes to it, you don't want others reading stale configuration. You want to kick people out from the connection, from the database, and only let them read when you're done editing, essentially, right? So so this way all the clients will always read the latest and greatest configuration value. So that's one of the benefits. The disadvantages of that, obviously concurrency suffers as a result. You can see like there are chances where you get failures, obviously, all the time, especially in banking system. You can see if you go to Banking America, sometimes you can see those grayed out. You can do any transactions at night, sometimes like at midnight, because they're doing their job reporting and they're doing all these shared locks. You can't really obtain exclusive lock at that time. But there are times that you cannot do your transactions. The concurrency cannot be achieved because of these locks. But at the same time, they are very critical to ensure consistency. All right, guys, this is in a nutshell. Exclusive lock versus share lock. I'm gonna see you in the next one. Have a good day.
Guys, my name is Hussein, and in this video we're gonna quickly show you a practical example of how deadlock happens in databases in this specific. So quickly guys, a deadlock happens when two processes or two clients are fighting for one or more resources, and either one is waiting for the other process to release the lock on a given resource, and they will be in this infinite state where nobody can release their lock. So it's a very famous problem in computer science. Obviously it happens in databases, and I'm going to show you how this happens. And most databases actually catch these deadlocks and fail the transactions when they happen. How about we jump into it? So before I jump into this video, guys, I want you to be familiar with locks, mainly shared lock, exclusive locks. And so if you want to learn more, check out the videos I've made about these topics here. Go and take a look at them. And with that said, let's just jump into this video, guys, and show you how. So I have here two clients terminal connecting to one Postgres instances running on Docker. I showed many times how to do that in this channel. Check it out. So in the first client, I'm gonna begin a transaction, and in the second client, I'm gonna also begin a transaction. Right? So both of them begin a transaction. There is a table here called test, and it has a primary key. It has one field and a primary key field. So you guys know if it's a primary key, you can only have one value at a time, right? A unique value. So I'm going to insert into this table, insert into test values. Let's call it, I don't know, 20, right? And that's successful because 20 doesn't exist, right? And I didn't commit my transaction yet. And in the other transaction, I am going to insert test values 21, okay? And that also succeeds because 21 doesn't exist. However, now in this transaction, I am going to attempt to insert 20. So 20 in this case, guys, despite it not being committed, there is an exclusive locks obtained on that value. Nobody can actually change that or insert that value again. However, we're not sure yet because this transaction didn't commit yet, right? So this might roll back or commit, and if that happened, this transaction will unblock and continue. However, let's spice things up here. In this transaction, I am going to actually insert the value of, you guessed it, 21. And now this guy is also gonna be blocked. However, both of them will be in a state where they are waiting for each other and a deadlock will be detected. The last one entering the deadlock will be the one to fail. So in this case, what happened here, Postgres immediately detected that. It took us like, I don't know, it took I think a second for that deadlock to be detected. And once that deadlock got detected, the transaction was rolled back, and that transaction actually won because it entered the deadlock first. So essentially, guys, that's how a deadlock is handled by the database. It's a very complex thing. Most databases handle these deadlocks very smartly, and they roll back the transaction that essentially entered the deadlock last. However, let's just explain a more optimistic scenario, guys. So I'm gonna roll back this. I'm gonna also roll back this. Clear here, and let's begin a transaction. And also here, begin a transaction where things like there's no deadlock. What do? Insert into test values 20. And here, I'm going to insert into test values 30. And here, I'm going to also insert into test values 20. And if I do that, I'm going to enter into this lock mode, and that's absolutely fine because until this transaction finishes, we are locked, right? So what happens if I do rollback here, guys? When I do rollback, immediately that transaction actually succeeds because the 20 is now available to be inserted, right? So if, however, we flipped this, let's flip it, and I do begin transaction here, begin transaction here, insert into 20, and here insert into, let's say 30, and then I'm going to insert into 20 here, which locks us, right? But here in this case, I'm going to commit. What happened to this transaction? Exactly, it's going to fail with duplicate key because now that this transaction actually gone, this transaction, in this case the 20 is not available, and we're gonna get that error, right, and fail, right? All right, guys, that was a quick video describing deadlocks and locks in general very quickly. Hope you enjoyed this video, and I'm gonna see you in the next one. You guys stay awesome. What is going on, guys? My name is Hussein, and in this video I would like to discuss two-phase locking with a practical example, guys. So two-phase locking is the idea of having acquiring database locks and releasing them in phases. Basically two-phase. The first phase is acquire, and the second phase is release. And the trick here, once you release, you cannot acquire. How about we translate all of this stuff to an actual good example, practical example with a very, very common problem called the double booking. So a double booking is where you're trying to build let's say a cinema booking system, right? And two users are trying to book the exact same seat at the exact same millisecond. And when that happens, you will end up with a double booking problem if you don't have two-phase locking or another implementation, right? And what happens here is the two transactions will get executed at the same time. They will both check the database, and they will both check that the seat is available, let me book it, and they will all both commit at the same time, and leading into problem with double booking. And that's extremely undesirable, right? Because you had two people paying for the same seat, and the last one wins essentially in this case, which is absolutely bad, right? So what we want to do is the first person who pays, we will immediately reject the second person. That's what we want to do. How about we actually jump into it and show you that at the database level, right? So guys, I talked about the double booking problem from a web application point of view. If you want to see more hands-on web application framework thing, check out the video I made here. But I'm going to talk from a database level perspective here. How about we actually go ahead and start transaction here? And we're going to go ahead and start transaction here. All right, so what I'm going to do here, this user is about to book seat number 13. So what it's going to do, it will ask to check if the seat is available or not, right? Select star from seats where ID equal 13 and says, hey, it's available. And the second transaction concurrently at the same time does the same exact thing from seats where ID equal 13. Hey, awesome, it's available. So what this transaction does is, okay, update seats, sit is booked equal 1 because it's now booked, and the name is now Hussein, where ID is equal 13. Awesome. So And the same thing happens on this transaction. So it's an update seats, sit is booked equal 1, name equal Edmond, that's the user here, where ID equal 13. Awesome, right? And you'll start seeing that this transaction is waiting. This is a specific behavior to Postgres. However, what will happen here is like the moment I commit here, this transaction also commits, right? And when I do that, I'm gonna go ahead and let's say select star from, before we commit the other transaction, I'm gonna select star from seats here, where ID equal 13. Hey, looks good. Send an email to the user that, oh, this seat is yours. But at the same time, the other transaction now just committed the transaction. And now the moment you select again, now the transaction belongs to someone completely different. So that's the double booking problem, guys, that we're trying to avoid. All right. So one way to avoid this is to do two-phase locking, guys, right? So the idea here is, how about we start again and do the two-phase locking here. So what I'm going to do here is going to do select begin transaction, and let's assume I'm going to book seat number 14 because it's not booked. And here's what I'm going to do. I am going to book seat number 14 here, and I'm going to also book seat number 14, but this time I'm going to implement two-phase locking. So what is two-phase locking? I'm going to obtain an exclusive lock on the row that I am about to update. And here's how I do it. I'm going to do select star from seats where ID equal 14. But what I add is for update. And when I do for update, select for update, that row, that object, that tuple will have an exclusive lock. So I am now in phase 1. I'm growing my locks, right? And the moment I do that, nothing seems different here. I still got my result, but there's something change here. We acquired an exclusive lock on the row. So that means if the second person tries to do the exact same thing, where ID equal 14, whether they do for update or not, look what happened. They're stuck. That's because they also tried to obtain an exclusive lock on the row itself, and that operation is now stuck because you cannot obtain an exclusive lock because that lock is already have been obtained by another transaction. That's the rules of the exclusive lock. And if you want to learn more about exclusive locks, guys, check out the video I made here. All right, so it says, okay, this transaction is happy now. It says, okay, update seats, sit is booked equal 1, name equal Hussein, where ID equal 14, and then boom. And once I'm done, I'm gonna commit. And look what will happen here. The moment I commit, this transaction is immediately unblocked. What happened when I committed? I entered phase 2 of the phasing of the two-phase lock, which is the release phase, the shrinking phase. The moment I committed or I lower back, what happened is I released that lock that I obtained here. So I said, okay, I changed it. Now it's safe for other people to read it. And that's what we want. The moment that transaction now reads this, it says, oh, this row belonged to Hussein. This seat belonged to Hussein. I cannot book it. So the user will get an error in this case. So your application will throw an error in that case. All right, guys. So that was like two-phase locking in a very short video to explain that. Again, guys, check out the other videos. What I put this within an actual application with a user interface and all that jazz. All right, guys, that's it for me. Very quick video today to show you about two-phase locking. I'm going to see you in the next one. You guys stay awesome.
Hey guys, what's up? In this video, I want to talk about how can you build an online booking system, and not just the actual act of building an online booking system, but the most important feature, which is prevent double booking or prevent race condition when two people try to book the same seat at the same exact millisecond. Okay, I've seen a lot of systems that actually don't have this problem solved, right? So I'm going to talk about it. I'm going to talk about how to prevent race condition. I'm going to talk about exclusive locks, right? And I'm not going to show you how I built this application because it's very straightforward, not really magic. I might make another video to actually show you how I built the application from scratch. It's really straightforward. I'm using Express Node.js and Postgres as the backend. I'm going to go through the application right now. The idea here is we are building an online system that books, I don't know, seats, right? You're buying tickets at a concert, and this is one user, and this is just another instance, maybe another user, right? And trying to open that. And these are seats. Seats are green, that means they are available. Red are booked. Okay. How about we actually try to implement this thing? So if I click on this seat number 3 and I say, hey, my name is Ali and I want to book this seat, I'm going to get back a message say, hey, this was booked successfully, right? And we're going to go through the logic and what exactly am I doing here. And if I do this and I'm refresh here, I can see that this now is booked by Ali. You can see there's a tooltip here. It's a bad front end, I know. It does the trick. And if I go to the other user and refresh, you can see that this has taken effect, all right? So if that user, let's say booked Jack booked number 9, and you can see that I am now actually debugging this, and I'm going to show you exactly what happened. So how about we go through the code? I made a put request here. And what we're doing here is we get the ID, which is the seat ID, and the name from the prompt. And I am connecting through a Postgres pool. So I'm going to pick up one client from the pool. And we talked about Node.js, Postgres, and how we actually make transactions. I'm going to reference the videos here if you want details. I'm going to go quickly through them. I'm going to begin a transaction because obviously this is a transaction, right? And the first thing I'm going to do in the transaction is this. I'm going to select star from seats. I need to actually query the seat and see if it's actually booked or not. That makes sense, right? A lot of booking system actually does that. And so where ID is equal 1 and is booked equal 0, that means it's not booked. And that's perfect. When I do this query, I'm going to get result back and the row count is 1. That means, hey, you actually found the seat and it's available for you. All right, so far, so good. But if that seat is not available, you're going to get an error. We're going to send back an error, seat's already booked. This is to avoid this double booking, but we're going to show that this is not enough in a minute, right? A lot of people actually do this part, you query and check that thing, but this is not enough. So I'm going to go, and once we actually pass this step, we are safe to actually execute an update statement and set the... Go away, please. is booked equal 1 and the name equal then where ID equal 1. We just physically set that statement. Sweet. Let's go ahead and just run this thing and we commit the transaction. We release the client back to the pool, right? And then we send the result. So we get back also here, booked successfully, right? And then if I refresh here, right? And I'm not going to refresh actually. If I actually click this 9 now, and I'm going to book it for, which is already booked. We know that it's booked, right? If I say, I don't know, Hussein, say, okay, we get an error. Failed, couldn't book because it's already booked. And the reason is because we have queried and that query actually failed, returned no record and got an error. All right, Hussein, what are you doing? All of the stuff we know. Here is the flaw of this design. The problem with this design is double booking can easily happen. Not on my single machine, obviously, but if you have a flux of requests coming at the same time, you will get into a situation where both statements actually at the same time, you can imagine them executing in parallel. They query, the seat is available, right? The first transaction query and says, oh, the seat is available, and it reaches here. And the second query also queries and also finds out that the same seat is also available, right? So both of them will succeed on this if statement. They will pass it, and both of them will execute the update. And that's the problem. In this case, last one in, but incorrectly, the client will get a message that actually your booking has been succeeded. We saw a lot of back maybe 10 years ago when online cinema became a thing, right? We always get double booking because of this problem, because it's a popular system, right? A lot of people query at the same time. So we're going to show how to fix that. First of all, let's reproduce this. Let's show you actually this is going to happen, but I'm going to do this with the power of debugging. So here's what I'm going to do. I am going to book seat number 15 now. And I am going to assign him to Rick, all right? And this will essentially go to the debugging statement, passes all of that stuff, and I'm going to pause it here. I'm going to intentionally not resume the code to continue. But guess what? It actually passed the select statement that actually checks whether the row seat exists or not. So the seat is available. Here's what we're gonna do. The seat is available, but that guy didn't update it yet. Rick did not actually reserve the seat because he didn't reach the statement, right? Now, if I go to the other client and I also try to book this guy and I say, Edmond, want to book this guy. I don't have a debugger. This guy will completely succeed because there's no debugging, right? It will query, find out this is available, and it will actually commit the transaction. Oh, this is booked now. Here's what I'm going to do. Now I'm going to just release the code. Go ahead and continue. And you can see that both of them actually booked the same seat, and that's the problem. This is what is called race condition in online system or double booking. And here is how we can fix this problem, guys, using the concept of exclusive locks. How about we jump into it and fix it? The problem here, guys, is both of these guys are attempting to edit the same row technically, right? So the solution, one solution at least, is the first person or process to get to the row should obtain an exclusive lock on that row so that the other process, when it tries to execute it, it will have to wait until the other transaction actually completed. And how do we do this in Postgres? It is very simple. The same thing you're selecting this row, right? The only thing you need to do is add two things at the end. So for update. That's it. When you do select star from select where ID and you query the row, you also say for update, and that is called a row level lock. And few databases actually support that, not all databases, right? So this is a very important feature in some databases. Postgres supports, I think MySQL also support it. Oracle definitely support it. And you do it for update, and the syntax SQL 92 is almost identical in all of them. So you do select star for update. Wow. All right. The moment you do that, the database will apply an exclusive lock on that row. That means if someone tries to update that row or select it for update as well, they will have to wait. And this is what I don't like about Postgres, right? In Oracle, because I use Oracle for 15 years, and in Oracle, that's why Oracle is expensive. One of the reasons is in Oracle, you can actually specify a timeout here. It says, hey, wait for 5 seconds, right? Here, it's actually an indefinite wait. I'm going to show that now in a minute, right? So let's go ahead and try to, now that we have fixed that, let's refresh this thing, and let's also rerun my second application, right? Which is AOM port 8888. And let's check this out, right? And for fun, let's just clear all that books, right? I'm gonna update seat equal book. What a DBA I am, huh? There's no one is booking anything just like that. All right, everything is now unbooked. Sweet, guys. All right, here's what we're gonna do. I'm gonna do the same thing. I'm gonna book seat 15. I'm gonna Edmond, for example, booking says 15. We go there, hopefully the debugger anytime soon. Now, okay, we selected the same stadium, but now it's for update. There is a little bit of difference in the database. It's freaking out now, right? We got it now. Here's the thing. This guy will always be the winner, no matter what. I'm going to find out how. So the other process now, we'll try to book 15. Was it 15? I think it's 15. Let's just make sure. I think it's 15. Yep, 15. All right. So 15, if I click 15 and I say, Melissa, want to book 15. Here's what we're going to do. Look at that. We didn't receive anything. It's just waiting. Now the process is just stuck. Right? And this is what I don't like about process. There is no option. I might be wrong, guys. Correct me if I'm wrong. There is no option to actually give up and time out after a certain amount of waiting, right? So this guy is waiting, and this is a bad user experience. That's the limitation of this now. And this is where your database actually shines. Now, if I go and say, release the Kraken here, go back, this guy, this is what happened. Look, ooh, something happened here, right? Booked successfully is the guy who actually, the person who actually made the transaction, booked successfully. But this guy was waiting technically right here. They were stuck. And the moment this process actually released the transaction, what happened is that lock got unblocked, and now we selected the brand new committed change, which was what it was actually committed, which was the rate is already booked. That means this result is 0. That means the seat is already booked. All right. And that's what happened essentially, guys. So this is now a bulletproof online booking system that is essentially race safe, or you cannot get double booking with them. Obviously, comes with a price. But that price, remember, nobody in their right mind will put a debugger, obviously. And this will take a finite amount of time, milliseconds. It's very fast. So the wait will almost be unnoticeable, right? So that's what you couldn't book, already booked. All right, guys, that was a short video talking about this. Let me know, guys, if you actually want me to build this application from scratch, showing you how I do it. All these pieces, we explained all that stuff before, everything, right? The GET request, this is a put. Also, for fun, I added a delete, but I remove it, right? To delete that booking, to unbook that thing. And obviously, this is very simple. I'm gonna reference the source code below for you guys if you're interested. And the database also, it's just a Postgres on Docker, very straightforward. And all the tutorials, all this Postgres tutorials, we have done them before. Let me know if you have any questions. Let me know if I missed anything. I'm gonna see you in the next one. You guys stay awesome.
What is going on, guys? This is a follow-up lecture on the double booking prevention lecture that I made on this course. And you guys had a lot of other, workarounds to solve the double booking problem, and most of them are actually fine. But one in particular that I actually liked, and I want to, explore, and I already answered this question many times in the Q&A sections, but words are very hard to express everything. It's always better to make a video and explain these in details. The reason I want to talk about this particular approach is the to understand how things actually work when you issue this update statement to book a seat, right? So what we're talking about, obviously, I want you to watch the double booking video before jumping into this video, right? Otherwise you don't have context. But if you notice, what we did is we were trying to book a seat effectively, right? And these are my seats effectively, right? And let's clear up these things. So let's say update seats set is booked equals 0, u equal null. So just clear out everything, so we don't have any other anything booked, right? So the idea, we're building a system that is, I don't know, Airbnb, cinema. We don't want to book a particular seat, and we want to prevent the problem with where two people book the same seat effectively in a way that last win in, which is the most dangerous kind of a situation, right? Two people pay for a seat and two people, kind of get the seat, but the last one actually gets the seat. That's very bad. So the way I propose to solve this is using this statement, which is select blah, blah, blah for update, right? Which effectively creates, takes an exclusive lock on the row so that this transaction is free to do all sorts of things until it commits, so that it releases the lock, right? And then the other transaction effectively, can resume, right? So this way you have full control to kind of isolate the transaction. You have full control to serialize the transaction. This is a very common way, right? But other people said, Jose, what if you did another approach where you didn't select to check the seat if it's taken and then acquire the lock, but no, just immediately do an update, right? And then check the result of the update if the seat was taken or not. This approach will definitely work, but I wanted to explain why it is actually working. And it's not actually guaranteed that it's going to work on all database systems. That's why I want you guys to understand the fundamentals. If you understand the fundamentals, you guys are basically unstoppable, right? Because you understand the basics. Throw any database at your on you, and you basically understand everything. So let's take an example. So I'm going to go ahead and begin a transaction here, and I'm going to begin another transaction here. And in this transaction, I want to book the seat for Hussein, right? Hussein is going to book seat 1, right? And in this transaction, let's say Rick is going to book the same seat 1. So what are you going to do? A lot of people suggested this, right? Update seats, set is booked equal 1. The user is Hussein. For which seat? Right? Sit for this seat, where ID, which is the seat ID, equal 1. And not only that, only when is booked is actually 0. When it's not booked and the seat is 1, go ahead and update the seat. So go ahead and now update the seat. So I'm going to go ahead and do that. And you can see that the transaction now successfully updated the row. Keep in mind, we did not commit the transaction yet. So now in the other end, someone exactly made the almost exact identical statement because it's executed from the application, right? But is booked equal 1, but the user equal what? Rick, right? Where ID equal 1 and is booked equal 0. And here's what I want you to think about what is actually happening right now. So here's what happened. We updated the transaction. We updated a row. Technically, we acquired an exclusive lock on the row. It's an update lock. So the row is technically locked. Seat 1 is locked by the transaction implicitly, not explicitly like the way we did it. It's a different way. Explicitly, when you say, oh, I want to select for update, I'm going to do stuff. I don't want anyone to touch my stuff here, right? So you're assuming that the database will acquire this and will not do anything for you. In this case, the database actually acquired a lock on the row for you, right? So the row is now locked. That is why when I hit enter here, the database, the transaction number 2 for Rick will be blocked. Now, why is it blocked? What exactly happened here? I want you to answer these kind of questions. And before you kind of pause the video and then answer these questions, now that you're in lecture, 65 or 70, you must understand these fundamentals. You must understand the isolation level, read committed, read uncommitted, row locks, all these stuff. You must understand it before. If you're here, you probably do because you watched the previous thing. So now what happened? We did a where clause because we want to update something. We did an index search, ID equal 1 and is booked equal 0. So what did the database do? Well, it depends. ID, I believe we have a primary key index. Well, Postgres don't have primary keys, but you get my point. It's a secondary key that points to the heap directly, but it's an index. So Postgres did a B-tree traversal on the ID index to find ID number 1. It found the tuple ID. And now it detected that this tuple is locked because of this the lock management of Postgres. Say, hey, wait a second, this thing is locked. I'm not supposed to touch it. So I'm gonna pause until, because I'm about to update it, right? I can't update it because someone is actually locking it, right? So you can read it, which we did, right? But we cannot update it. So now the question is, if we read this, right? We didn't go to the heap. We're still in the index. If we did go to the heap, right? What do you think the value will be of the booked, right? The value of the booked here is actually 0. It's not booked yet. You might say, Hussein, we just executed the transaction. No, yes, we executed the transaction, but this transaction is isolated. It started at the same time, right? So this guy still sees the row as unbooked. So that's why it managed to actually fetch that row. So now we fetched that row. We found that this row is actually, unbooked. So I can actually fetch it. But when I tried to update it, I failed because there is a low lock on it. Now, what happens if I commit my transaction here? When I commit my transaction, 2 things will happen, right? It's like, it really depends on you are at the mercy of the database implementation. You're at the mercy of the database implementation at this end, right? Because the moment I do commit, the row will be locked. It will be released, right? I'm going to change these values and make them committed. So the row now will belong to Hussein, and the booked value is going to set to 1, right? So what will happen on this transaction, right? Well, the transaction, because remember, the transaction already seen the row unbooked. Is that even a word? Unbooked? Not booked, right? So what will happen here? Right? Let's see what happens. We committed that, and immediately on the Postgres on the other end, it did not update it, which is exactly what we want. That's the desired behavior. But why? If you really think about it, Postgres here did a trick, right? Sleep off. Yes, it is a little bit early here. Right. So Postgres did a trick here. It actually refreshed the row to look at the final result, right? And then when it detected that, the final results actually is booked equals 0. No, it's not, right? Why? Because when we did that, when the transaction was running, the row was actually in fact not booked. But the moment this transaction committed, now the isolation level changed. Because this is read committed, right? I'm allowed to read committed values that are here. So now, only if your isolation level is read committed and the database actually refreshes the values of the row upon committed, so now you can actually read the values here and make the decision as a result, right? So, and what I'd like to add is something I forgot to add here is I remembered after editing the video, is Postgres actually stores the knowledge about lock information in the row itself. It's just another field in the row, and these columns live where? Obviously in the heap, right? So when we go to the heap to fetch the is booked value, that's when we looked at the lock information, and we obviously jump to another sort of data structure to fetch the value that is actually locked or not, right? That's when the database, the transaction decided to block itself, right? So that jump is very critical. And when the row has been released, what happened here is Postgres refreshed the heap value. It actually said, okay, yeah, I'm blocked, but I cannot just resume. I have to kind of re-execute the query in a sense, right? To see the actual values. Yeah, at a given point, it was not booked, but now, how about now? Is it actually booked, right? And yeah, it depends on the implementation. And that's what I wanted to clarify, right? This is how Postgres does it. MySQL does it completely differently, right? SQL Server does it completely differently. They look in memory. And can you guarantee the same result? Absolutely not. You might get lucky, right? If you execute this query and you see that SQL Server or MySQL does it this way. But I wouldn't, unless you're absolutely sure that this is how the database implemented this stuff. Now you're at the bowels of the database implementation, and basically this is the power that I want you to have as an engineer, as someone who actually learning database engineering. Just understand that this is all code, you know, it's all written by human. They make decisions. They get emotional. They write one piece of code. They get emotional. They write another piece of code that could get broken. You know, nothing's perfect. Whatever we're looking at is written by human, you know. And this is what I want you to break. Because when I first learned database engineering 9 years ago, I was also always, you know, getting intimidated by all these terminologies. But once you really understand what's going on, you're basically unstoppable, because you understand you're gonna ask the right questions, guys. And when you ask the right questions, if someone actually understands, they can reply back to you, and that will guide you to the answer. You know, don't take things as surface value. Always understand, always ask questions, and the nature of the questions you ask. And I start to see some people in this course actually ask these kind of questions, you know, dig deep. They kind of dig deep and try to, okay, why is it doing this way? Why is it not done this way? This is the great questions, you know. Nothing is perfect. Nothing, absolutely nothing is perfect that you see now. Anything that is there is being done by a human, and human are imperfect by nature, right? So I know this got philosophical a little bit, but I really want you to understand this, you know. Just ask the right questions, you're gonna get the value, and as a result, you're gonna find the answer, right? All right, back to the video. In that case, it detected that, oh, the row is actually, oh, yeah, it's ID number 1, that's true, but it's booked. Right, so that statement is false, which will break the condition. I cannot guarantee what will happen in Postgres if, for example, both of these are actually indexed. You created a combined index where those two guys are actually in the index, and you search in the index and you found the values indexed, right? And you found you did a search before that, right? And you found that the row is actually not booked. The Postgres might decide to say, hey, it's not booked. Let's go ahead and commit. You will never go to the heap to see the actual updated value, or maybe it will, right? So that's why I'm saying that this will definitely work, but you really need to understand why it actually worked. Not because we're filtering on this. No, it worked because of the database semantics and the ACID transactions, and there's so many other things that you really need to understand in order to get this. So yeah, definitely you can use this, but the downside of using this approach is, first of all, you need to be in read committed mode to do that. Second of all, you really don't have much control when it comes to this transaction. You're at the mercy of that particular update statement. But what if you, for example, want to do multiple things, right? I want to book that. I want to take a look on that row, right? And then do multiple things in this case before I commit. So with explicit locking, you have a little bit more lenient way, right? Database doesn't do like implicit things for you to behind the scenes that you don't understand, right? So I kind of prefer the for update approach, but this definitely work. And obviously, as some people said, this is kind of more efficient. I'm hesitant to say that, but it's just that in this approach, we're also taking a lock, but the lock is a database internal lock, not a user lock that we have maintained, right? So there will be a lot of cases where you take a lock that you basically didn't need to take, right? But again, At the end of the day, Postgres and other database system is a pessimistic, pessimistic concurrency control, which means they always take a look, right? They always take the umbrella with them, as I always say, right? They always take a look, and at the end of the day, managing locks are expensive, but when you manage the locks, right, you take that, you be protected from these kind of situations. Other approach where you become optimistic concurrency control, where, hey, I'm not going to take a lock, right? But at the end of the transaction, I'll detect the change and fail the transaction. I prefer pessimistic personally because, I don't want to retry my transactions. I know NoSQL databases always prefer that approach. Nothing wrong with that. I just a personal preference at the end of the day. I don't like my transaction. If my transaction will fail, I want it to fail for the right reasons. I don't want it to fail because of a concurrency problem, right? Because that's just another condition in your application that you have to take care of. All right, guys. I think that's it for me today. Hope you enjoyed this video, and enjoy the course. Goodbye.
In this video, I'll explain why you should avoid using SQL offset when implementing any kind of paging. I'll explain what offset does, why is it slow, and what is the alternative for better performance. This video is inspired by Use the Index Luke, and I'll have a link to his blog and slides to learn more. And if you're not subscribed to Use the Index Luke blog, what are you doing? This is an extremely mandatory blog to read for all database engineers. So check it out. So let's say you have a web application with an API that supports paging. Your user wants to request 10 news article in page 10. This is performed via a simple GET request as shown here. The API server receives the GET request and builds a SQL in order to send it to the database. Hopefully there should be a pool of is already established TCP connection to your databases, so you don't have to hit that cold start problem here. Page 10 translates to offset 100, assuming each page has 10 records, and now the database is ready to execute the query against this beautiful table. Offset by design means fetch and drop the first X number of rows. So in this case, the database will fetch the first 110 rows and physically drop the first 100 because guess what? You said it's offset, right? And then leaving the limit of 10 rows, which the user will be actually seeing, right? As the offset increase, the database is doing more work, which makes the operation extremely expensive. Another problem with the offset is you might accidentally read duplicate records. Consider this. The user has now requested page 11, which is now offset 110. And meanwhile, someone inserted a new record in your table. So now offsetting 110 rows will accidentally push your existing row that you have read before to your result set. Accidentally, now all of a sudden you just read a row that you have read before, which is row 11 in this case. Let us jump to the practical side and test this thing on Postgres, guys. Alright guys, I have a Postgres database and I have a table called news, not test. And there is an index on the ID. And I'm going to use the ID here as since of it as like a auto incrementing ID for my news articles here. And don't pay attention to these three fields. This is the title of the article essentially. What I want to do here is I'm going to use offset
to start paging this. And I want to see how the database performed as a result. All right, so let's start with explain, analyze, select title from news, order by ID descending, because I want the fresh news first. And then I'm going to start with offset 0, and then I'm going to limit the result with 10. And then when I do that, instantly I get the results. Obviously, we have two results. Let's explain what happens here. We're using index scan backwards, right? Because I did the order by ID descending, and index is already ordered by default. So the index was scanned backward from bottom up, I guess. And then there is this much rows in the index, but this is not really what we actually pulled is 10 rows. Why? Because offset 0 plus 10 rows, that is exactly 10. And applying a limit on top of that, giving you 10. So that's not so bad. It took 0.2 millisecond. But let's spy things a little bit. Let's start with offset 1000. And all of a sudden now, look at the rows here, guys. We have pulled from the index 1010 rows, 1000 plus 10. And that, on top of that, we applied a limit, and then we only pulled 10. You're seeing the pattern. Took 1 millisecond, right? That's not so bad. Let's make it 100,000. Ooh, you started to feel like 79 milliseconds. And guys, I run these queries many times, so there's a lot of page caches. So this might be slower first round, but you get the idea. So what happened here? We pulled 100,000 and 10 rows, and then only from those stinking 100,000 rows, we pulled 10. Can you imagine the work that the database is doing? Guys, think about this. This much rows, if this was SQL Server will immediately escalate the lock. It says, oh, we're touching this much rows, but who's gonna die? But Postgres, thank God, it doesn't do lock escalation, right? So look at what's going on. We're working with 100,000 10 rows. We only actually need 10. And the unfortunate thing, the database doesn't know to do this because it's too late by then. All right. So you get the idea. Do 1,000,000. And you can start feeling it. It's going to be slower and slower, right? And if I restart the database, this is going to go so much slower, 620. And the first time I ran it, took like 6 seconds, right? But you get the idea, right? Now, what can I do to fix this, guys? So what I'm going to do, I was going to do a little bit nice trick to actually accomplish that. I'm going to remove the explain analyze, and I'm going to remove the offset, and I'm going to simulate an offset by using the ID itself. And then since the ID field has a beautiful index, I'm going to use that as a page. Look at this. So there's not really rocket science what I'm doing here. I'm going to select the title and the ID, and let's say I'm going to pull the first 10 rows. And you return this to the user, right? And the user is responsible now to send you what was the last ID it saw. It saw or sees? It saw. It's past tense, yes. So now, what you do is basically execute the same query, but says, hey, don't bother returning anything after this ID. This is the last ID I saw, so I want older pages because you're going back, right? And it depends like how you go forward or back, right? You can play with this in your algorithm. But if I do this now, I got only these rows. And this is much, much faster. Let's take a look at the explain analyze. What are we doing? Explain analyze. And if I do that, look at the number of rows that the actual database worked with. Only 10. Why? Because if you do just limit 10, that's the best thing you can do. This is good. You didn't use offset with it. Using limit with two parameters like 10, 10 or offset, that kills the performance because now you have to jump and then read. Limit 10 tells the database, hey, I'm looking only on the first 10 rows that you can pull. There's another command called fetch first rows only, whatever, the first 10 rows. That's another thing you can use it, which is exactly the same as limit. All right. So if you do that, then you get back 10 rows. The index will be scanned backward, but it says, wait a second, we only need 10 plus we have used an index to actually filter that even down even better, right? We just essentially filter down the results, right? We're working with a little bit of a more niche result, which is awesome. And now, and the limit applied after the limit only took 10. Now, if I do this, if I imagine went back all the way to page, I don't know, 1000, right? Page 1000, which is very, very old. Guess what? Instant, right? We have worked, now the database worked with 89 rows instead of whatever, right? But still, the actual results set from the index came out as 10. Now we jump back to the heap, we pull the title field, and then we limit, and it becomes 10. So the amount of I/O is much, much less. The amount of work that the databases do is way less, and you saved a lot of CPU cycle, and the database will thank you. Hope you guys enjoyed this video. Guys, what are the other approaches that you personally do when paging? I'd love to see them in the comment section below so we all can learn and advance and become better software engineers. I'm going to see you in the next one. You guys stay awesome. Goodbye.
Connection pooling is a pattern of creating a pool of available connection, usually TCP, and allow multiple clients to share this pool of connections. This pattern is usually very useful when connection establishment and connection tearing down, connection security is particularly expensive, which is the case with databases, right guys? And that's also useful when the server has very limited number of database connections, right? And you have a lot of clients. So what do, right? In this video, we're gonna learn how to do this classically by basically creating a REST API. When you make a GET request, you establish a connection in the backend, a database connection, and then make a query and then close it. It's like the old, really bad way of doing things, right? But it's a stateless nevertheless, right? So another way we're gonna do it is like we're gonna spin up a pool of database connections. We're gonna just call the pool.query, which will pick up a random connection, okay, from this pool, and then execute our query. So that's what we're gonna, and then finally we're gonna perform some performance numbers between the stateless approach, which is like every request opens and closes the database connection at the backend, and the pool connection pooling request. All right, guys, so I have locally here a Postgres database, and I have pgadmin, and I have a Postgres database here with a database called HusseinDB, and I have a table called employees, and those are the employees. And here's the old approach of doing things, guys. All right, guys, so I have here an REST endpoint that I have written, and this hits the back end, which we're gonna show the code in. And what that does is every time I hit enter, it makes a GET request to the /all, which in turn establishes a database connection with the Postgres database, execute the query, select star from employees, return the rows, and then closes the database connection. Every single request does that, okay? So, and that's what we get back. Beautiful REST of JSON with all that fancy dandy stuff, right? So what we're gonna do here is, it also tells you like the elapsed, how long it took, and the method. That's I just added some more metadata here. So let's go over to the code and show you that how we used to do things. All right, guys. So this is the back end here. All right, and I'm using Express, obviously, and the PG library. So what we do is like get a client, and when someone executes /all, we just snaps the time before the execution, open the connection to the database, just provide the library. So that's the database, Hussein, the username, password, port, all that stuff. And then connect, that establishes the TCP connection. So there's like three-way handshake and all that jazz going on, the protocol handshake. That's expensive. That's very expensive, right? But we're doing it. Every GET request, we're doing that. And then we establish a query. We make a query to the database. That's the worst query ever. Never, 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 ever, ever do this, right? In production, select star is bad enough, and unbounded query is even worse, right? Always have you'd have to do proper paging with these kind of things. You get back the results, printed in a nice table like that. Close the connection, also expensive, right? Just like releasing the file descriptor and all that stuff, and then get a new time because we're just done. Get the elapsed time, and then return the rows and just tell me how long it took, right?
And that's it. Very simple stuff. So how can I rewrite this using the pooling approach? So let's go ahead and create a brand new file called pool. Yeah, okay. So I created this pool.js. And here's what we're going to do. We're just going to copy the whole code. Same thing. Because it's very minor, the changes really here. And here's what we're going to do. And instead of creating a client, we're going to create the pool. We're going to get the pool class. And instead of creating a client object, we're going to create a pool object. And obviously, this is bad to have it in every request. We want to execute it once when we start our server. All right, so we're going to replace the client with the pool. And here's the thing. It's a pool, right? So how many connections do you want? There's the first parameter, which is called max, all right? And the max parameter is how many connections do you want by default? The default, I believe, is 10, right? But you can specify any number based on like how healthy you want your Postgres database to be, right? So you specify a number and it's gonna manage those connections. So that's the maximum number of connections it will allow you to create. You don't control that anymore as a user. You just ask the pool, hey, execute this query for me. It will pick one of those 20 connections, right, and execute a query. If there are no connections left, all of them are being used or busy, right, you're going to have to wait as a client, right? And there is a timeout for that, okay? And that timeout is called, let's add both properties and let's talk about them. So there's the connection timeouts, right? After which the default is 0. So how long I should wait for a pool to give me a connection if all of them are busy? 0 means wait forever. You can decide to shorten this time, right? And the final one is the idle time. I believe the default is 10 seconds. What idle timeout means essentially is after establishing the connection, if those connections are not used, when do you want me to get rid of it? Because it's a memory, right? So it's staking memory. It's using these file descriptors and it's staking memory. So when do you want me to destroy it? This much time afterwards it will destroy. 0 means it will never get destroyed. Okay, so now we have this connection. Let's go back to our method. We no longer need a client.connect anymore, but you can ask the pool to give you a dedicated client and then you release it, right? That's especially it's good for using transactions. We are executing almost like a stateless queries here, so I don't really care which one do you want. So I'm gonna choose the pool.query and query. You ask the pool to execute this query, and the pool will take care of which connection it will use to execute that query. Get back the results. We really don't need to end the client because there's nothing here. And what we want to do here essentially is give the time and then get back there. And the method is not old, it's the pool method. And that's it. Let's test it out, guys. So I'm going to change the configuration to the pool.js. Let's go ahead and run. So what are we gonna see? You're not gonna see any different, guys, but let's take a look. So if I do now /all here, right? You didn't see any difference. It gives you the same results, obviously. But now this is using pooling. So it's actually faster because those pools are already available for you. And it will gonna pick that, and then there's no overhead of establishing and closing the connection every time. So that's always a better approach to do that, okay? And the Node.js is since it is a single threaded application, it's a non-blocking as well. So it will, despite having single thread, it will manage all these connections for you without actually blocking this thing, which is pretty cool stuff. So what can we do to prove that this is actually good, right? So here's the thing. I'm gonna go ahead and actually create an all.js file with both methods, right? So what I did is like I did a /old method which execute our old pattern and give us the time and the average as well, how long it took after, I don't know, the total number of executions, right? I'm gonna sum all the attempts and the time it took and then take the average of the time, and then I'm gonna report the average over the time, and then I'm gonna do the same thing with the pool, right? So, and then on the client, we're gonna execute like 100 queries, right, on the pool and 100 queries on the old, and see the average between the two. How about that? Does that sound good, guys? The code will be available for you guys in the description below, so you don't have to like pause the video and do all that stuff. So all.js is has now, it's a very interesting 2 endpoints. slash pool endpoint to use the pool approach, slash old approach to use the old approach, which is always a stateless closing, opening connections every time. So let's go ahead and do that. Now we're doing the old. Let's go ahead and test it. If I do slash old, get the result. If I do slash pool, I get the result. Still, I don't see any difference, but if I go to developer tools, and here's what I'm gonna do. I'm gonna do a loop, let's say 1,000 against the old. 1,000 is all bad much, but sure. Execute. And you can see that it is actually querying, and you can see the average of the old is around 40 milliseconds, right? And we are getting a lot of requests. Almost done. I think done. All the 1,000 queries has been executed successfully, right? So we have just created and destroyed 1,000 TCP connection in the backend, right? That's surprisingly fast, right? Especially for a local database connection, right? If it's remote, you're gonna be even slower than that. So let's go ahead and change my approach to use pool. Hit the pool, right? And that will do is like do a fetch and then just expect a JSON and then just let's see how pool is doing. Oh, that is way better. 40 milliseconds versus 19. Oh, it's going down. Nice. So I can see, guys, it's almost like 50% faster. And I guarantee you, if you move to a remote database, like in the cloud, it's going to be even more than that, right? And the reason is like the more connections you have, it's even getting better and better, right? So it's like almost like a resource issue, right? That's a stateless query that we have explained, right? So we just query, but sometimes you want to execute a series of queries in an ACID manner, in an atomic manner. And to do that, you can ask the pool to give you a client and you can lock that client for you and then execute multiple queries, right? I'm going to see you on the next one. You guys stay awesome.